Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with Microwave Engineering second chapter, Microwave Linear Beam Tubes. In the family of these linear beam tubes, we have already understood the two cavity klystron, multi-cavity klystron, reflex klystron, and now we are dealing with the helix type of traveling wave tube. Working operation based on to the velocity modulation we are already covered with. In the previous video, we have gone through the wave modes in this particular traveling wave tube. So we have the four waves. So based on to it, let us study the gain considerations. So here we start with our topic, gain consideration in TWTs. In the previous video, we have gone through the understanding that the wave propagation based on to the helix and then its interaction with the electron beam that is having the axial direction to the orientation of that helix will be having the amplification process. And for that particular wave propagation, we obtained the four types of waves, the three into the forward direction with the representation of the complex exponential e to the power minus j beta suffix e into z. So we have considered the positive z direction for the propagation, and for the one backward wave it was considering the complex exponential e to the power plus j times beta suffix e into z. So beta suffix e is the phase shift constant with respect to the electron beam. So for obtaining these, we have set the phase velocity of the electronic signal there, that is actually to be amplified, the microwave signal approximated to that of the DC electron velocity, and it was all done in terms of the propagation constant gamma, and finally with no losses we assumed gamma 0 to be equal to j times beta suffix e. Now to look at the gain consideration, out of the four waves, the three forward waves are helpful to us. We don't want the backward wave. The basic structure of the traveling wave tube we have gone through. So in that basic structure you have seen that at the center of the helix the attenuator is provided. So though in the analysis we come to know that there are four waves, the fourth wave, that is the backward wave, is normalized and there is no effect of that particular backward wave. So finally the voltage provided by the traveling wave tube operation is because of only the three forward waves. Therefore we can write here for the total circuit voltage, we can say the circuit referring to the slow wave structure of helix. So it will be capital V and it will be a function of Z. So for the first forward wave, it will be the first term capital V1 into e to the power minus gamma 1 into Z. So gamma 1 is the first propagation constant that we have formalized into the last video. Then it will be the contribution of the second wave there. So it will be having the second term. There we represent V2 into e to the power minus gamma 2 into Z here. So now the third wave, that is of course a forward wave, will be contributing with the third term here. So these two terms will be added with capital V3 into e to the power minus gamma 3 into Z here. So therefore using the summation representation we can simply write capital V as a function of Z, the total voltage developed given by, here we have summation operation with the index term n is equal to 1 to 3 here, operated over V suffix n into e to the power minus gamma suffix n here into Z here. So this is the very important equation. Let us say this is equation number 1. Now the input current can also be obtained to look at the convection current of the traveling wave tube that we have computed into the last video. So as a function of the length z, I of z, the input current can be represented, and here it will be having minus summation sign. Again the index term is n is equal to 1 to 3 here, and here we have the representation of capital I0 divided by, here we have twice capital V0 into the gain parameter C, that is squared here. In multiplication to it, it has Vn divided by del n, that has the power 2, in multiplication to the complex exponential e to the power minus gamma n square here. So this equation is also importance as it is for the current here. Now in this particular equation we have the condition C into del, that is very less than 1, along with the maximum magnitude of the axial electric field E1 will be equal to gamma into V, whereas gamma is put equal to J into beta suffix E in the bracket. Here we have 1 minus C into del here. So we have the representation with respect to the voltage, with respect to the current. Now the representation of the fluctuating velocity that represents any general electron into the electron beam. So this equation as a function of distance z can be represented as V1 in bracket z computed as summation operation with index term n is equal to 1 to 3 for j in multiplication to the DC electron velocity small v0 divided by twice capital V0 into C into, here we have capital V suffix n divided by del suffix n into e to the power minus gamma suffix n, and the gamma is squared here. So the fluctuating velocity here we have represented with capital E1 as before, given by gamma into capital V, the condition C into del, that is very less than 1, the product of phase shift constant beta suffix E into the DC electron velocity V0 will be equal to omega, whereas this DC electron velocity V0 is governed by the equation that is totally dependent onto the DC potential, that has twice E by m ratio in multiplication to capital V0. Now in order to see this amplification with respect to the gain consideration, here we set 2 points. For the input with respect to the length we take z is equal to 0. So this is the input reference point, and as far as the output is concerned we set the reference at z is equal to small l. So this is the output reference point. So with respect to these two reference points, here we have the representation of first of all the overall voltage. So voltage will be represented for first of all the input reference point V in bracket 0 can be given as simply it will be V1 plus V2 plus V3. Also the current that we can give for the first reference point, so here it will be I as a function of 0. So at z equal to 0 we have the computation of the current. The formula modifies to minus I0 divided by twice capital V0 into C in the bracket. Here we have capital V1 divided by del 1, that is squared here, added with we have V2 divided by del 2 squared and V3 divided by del 3 squared here. So along with this voltage and the current for the input reference point at z equal to 0, we have the representation of the fluctuating velocity. So V as a function of z we had earlier introduced in the representation. So we put z equal to 0 in this equation, and it will be given as V1 in the bracket 0 for the case of ZVQ, and it will be minus J in the bracket. We have V suffix 0 divided by twice capital V suffix 0 into C in multiplication to the bracket has V1 divided by del 1 plus V2 divided by del 2 plus V3 divided by del 3 here. Now we have the three equations we have taken for the input reference point for the voltage, current and the velocity. Now having the simultaneous solutions with respect to these three equations, we can obtain for the conditions. Here we have I of 0 equal to 0 and V1 of 0 equal to 0, because at the initial condition there it will be electron only generated, not into the motion, hence it will not be constituting any current. Therefore capital V1 will be equal to capital V2, it will be equal to capital V3 and it will be equal to V in the bracket of 0 divided by 3 here. So it is the average, we can say, for the three waves. We shall be obtaining the amplified output. So in terms of voltage, the amplified output can be represented by the equation. So that equation will be capital V. In place of Z, I put the output reference point, that is small l, as the length covered here. So it will be approximated to V of 0 divided by 3 that we have averaged just now, into the exponential that has under root 3 by 2 into beta suffix e into c into the length L here represented into the exponential, for the bracket here we have minus into j times the phase shift constant beta suffix e in multiplication to the bracket 1 plus c by 2, that is having L in multiplication 2. So I complete this particular bracket. So this is really very important. Now in this particular equation, there it is a factor beta suffix e into L that can be conventionally been written as 2 pi into capital N, where capital N is most of the times termed as the circuit length. Circuit length, or as far as the slow wave structure we have taken to be of helix type, it is number of turns. And with respect to the wavelength here, we can write capital N will be equal to the length L divided by lambda suffix e here. So it is the wavelength with respect to that of the electron beam here. And we have the phase shift constant beta suffix e, it will be equal to 2 pi upon lambda suffix e here. So basically the phase shift constant is actually a ratio of 2 pi phase covered into one cycle of wave. So that is, for the wavelength we have the representation of lambda here. So therefore the amplitude of the output voltage can be denoted here in simplified form, V as a function of small l computed as V of 0 divided by 3 into exponential of, here we have under root 3 times pi into capital N into capital C. So now we have the input voltage as well as the output voltage. Input voltage as the Z equal to 0, that is the input reference point, and output voltage as for the Z equal to L case. Therefore we can write down the output power gain. So output power gain we can denote capital A suffix P here, and it can be simply representation in terms of decibels, that it will be 10 log to the base 10 for the mod ratio here V of L divided by V of 0. So this mod is squared here. And by the next step we again have some simplified formulation, that the calculation gives minus 9.54 plus 47.3 into capital N into capital C after substitution of the numerator and the denominator. So the output power gain we abbreviate here with this simplified formula. Now to look at this particular formula for the output power gain, the first term gives us a negation of 9.54. So this term is actually appearing because as we have the input wave that has been getting splitted into the three forward waves, but for the growing case of the amplitude, there it is the average of the three. Therefore this is the initial loss we have. But another thing we can notice that the output power gain is actually directly proportional with respect to the circuit length represented by capital N, the number of turns, and the gain parameter capital C here. So these were the gain considerations with respect to the device traveling wave tube. The working operation we have already covered, the wave modes and gain considerations we have seen with respect to this device, and based on to this understanding, by the next lecture we shall be having problem number 1. So I hope you are definitely getting the details of the microwave engineering very well. For more information like this, you can subscribe to Ekeeda channel. Thank you.